My name is Mark Laufenberg. I'm the president of PowerWorld Corporation. I'm going to be your host for this meeting today. I'm hoping everybody can hear me okay. The schedule for today is that we're going to have a presentation by Jamie Weber about the results analyzer in transient stability. It's a very detailed and in-depth presentation and should have a lot of interest to those of you who are active users of the transient stability portion of the PowerWorld program. And then we will have a presentation later on from Scott Dahman about the developments recently in the GIC tool, especially related to reading in some different types of files, other developments that have been going on. For those of you who were here last week, we made a pitch last week that you should, if you feel the desire to do so, you should contact Scott Dahman and ask to be added to our beta testers list. We are in the process right now of working on version 22 of the software. The release date, we don't feel more comfortable than saying anything more specific than sometime later this year, the release date for version 22. However, we do feel comfortable enough to get a list of beta testers and start to get the version 22, the beta version of the version 22 out to folks. So if you have any interest in that at all, it always really helps us to have beta testers because that allows us to do testing before the release. And again, please contact Scott Dahman in order to let him know that you're interested in that. Email is just scott@powerworld.com. One other thing I'd like to ask everybody to kind of mute themselves if they're not talking. That always helps with kind of the background noise that we have going on. I do have the ability to mute folks here, but I don't want to accidentally mute somebody if they do want to say something. So please do mute yourself if you're not talking. The chat window will be available and be open. So if you have any questions while Jamie is talking, you can either just say them and that's fine, or you can put them in the chat window. It seemed like we made pretty good use last week of the chat window, and we do have several PowerWorld Corporation developers online here today as we speak who should be available to answer some questions. So feel free to make use of that while Jamie is talking about his results analyzer, or if you want to, just feel free to interrupt him as well. That should be okay too. Okay, with that, I think I will turn this over to Jamie. Jamie, take it away.
All right, 1 second. All right, this is going to go over looking at how do you look at the results of a transient stability run. So PowerWorld has a lot of tools that have always been there in our transient stability tool, including just plotting, transient limit monitors, the min-max results for just looking at statistical information about some hard-coded values with buses and generators. Those are all very useful. I'm not going to talk about those because we don't have time today. What we're going to look at today is how do we detect oscillations. So power systems, all of you know, have oscillations that occur. There'll be sort of 1 to 5 hertz oscillations are kind of like local generators or maybe some generators nearby oscillating against each other. Transients would be things like switch shunt switching, things that are, tens or dozens of hertz. Those are things we don't really study in the transient stability tool. And then inter-area oscillations, like kind of north to south and west, or Alberta to the rest of WEC, will be in the tenths of a hertz. And then even slower dynamics that could take minutes long, like AGC and stuff. So, I stole a couple slides from Tom Overby's presentations where he shows this is the California-Oregon intertie in a blackout event from 1996. The actual event caused an oscillation that caused the system to separate. The simulations didn't show that in that example. So that same kind of things happened for the blackout in 2003. Honestly, this one isn't as interesting because by the time they got to the point that things were oscillating like this, it was hopeless. So, there was nothing to learn there, except don't have things happen earlier on. But the point is there are some oscillations that one could detect in a power system. So really starting the result analyzer in PowerWorld kind of started from two things. The first I'm going to talk about briefly, and honestly might be like 50% of what the user community are going to use it for, even though it's simple, honestly, because it's so simple. I got a lot of comments of, I love this min-max reporting, but is there any way I could specify a time window? You know, maybe I want to monitor the generator megawatts between 5 and 10 seconds, and I want to monitor some interface flows between 10 and 15 seconds, and I want to be a little more flexible about when I report this statistical information. The other question that people had a lot is, I want to know, is the system damped? It's like, is it an oscillation that is damped? So those two requests both require similar input into a software tool, and they led to the creation of the Transient Result Analyzer. So in version 22, we thought the transient stability dialog was too simple, so we thought we would add yet more to it. So on the downside, there's a bunch more tabs on it, but there's a thing under plots for the result analyzer and defining these time windows and statistics and damping and modes that we'll go over in this presentation. All right, I'm going to go through some theory here. So the first thing that you need to do when you're either calculating the statistics or doing this modal analysis is you've got a set of results over time. You need to specify a window over which you're going to monitor or perform calculations on it. So in this example, I'm saying between 7 and 10 seconds, I want to take these signals and I want to, get statistical information about them and do some modal analysis. So first, the easy stuff. I don't even really need to explain this. You can imagine you've got a time series. I just want results that tell me what is the max value, what is the min value, what is the max increase, what's the min increase, what's the average, what's the standard deviation, and just spit that data out into a table. So that's the first thing that we do. It's easy stuff. Inside simulator, I'll show this in a little bit. You get a table that lists all the signals that you were looking at. So in this example, it's a particular contingency, and I'm monitoring a particular field and object and a set of them, and then it'll give me the mins and maxes and the max minus the min, all this statistical information. And you can, click on there's a dialog that brings up, here's the max and min for this particular signal, and the statistics are available there. So, there's very little to talk about. Everybody here understands how to calculate an average. So we're not going to talk a ton about this, but I do want to just kind of emphasize up front that even though I'm going to spend the next hour talking about modal analysis, which is way more flashy for a presentation, my gut feeling is half of what is useful in this tool I have already covered, and that many of you are going to use this. It's much more flexible. You can monitor anything you monitor in plots, anything in a transient limit monitor. So, it's very easy for you to understand. It's very easy to explain to your boss. So the result analyzer will be very useful, if only for that. But like explaining how to calculate an average, I don't need to do. So, all right, on we go to the modal analysis, which is really the primary topic of this presentation. All right, so the first thing we need to talk about when somebody says, is a signal damped? We kind of have to define what that means. And the first thing we need to define is, what is a signal? All right, in our purposes in transient stability, I would define a signal as a time series of a numeric value. It's just like the generator's speed from 3 to 10 seconds. That is what I would define as a signal. All right, the mathematics that I'm going to kind of wave my hands at in this presentation, it it all comes from very broad backgrounds. You know, a signal, if I'm an image processing engineer, is a spatial sequence of colors. And they would use the exact same algorithms I'm going to present today. Well, I'm not really going to talk about it. I'm just going to kind of mention there in the background. Audio signals, facial recognition, pattern recognition, all of these things come from the same mathematics, but again, that's not what we're talking about today. So for our purposes, you know, me and you as a power system engineer, this is a signal. It's a squiggle on a plot. It's a time series of numeric values. So the next thing is, well, how do I describe the damping of that signal? Is this damped? You know, I can look at it and say, yeah, that signal's damped, but how do I describe it so that I can run a computer software program to tell me it's damped? So the first step in doing that, in the way we define them, is to do what's called modal analysis. All right, not really going to talk about how the mathematics of finding these modes is done in this presentation, but I do want you to understand what a mode is. So a mode, one mode, is and again, for the way we define it in power systems, is just a sinusoidal, so it's a cosine, multiplied by an exponential. So a picture of it. So if, you know, the cosine portion is defining, you know, how fast it moves up and down. The exponential portion is describing the magnitude. So it's describing the envelope of this cosine wave. So if this lambda term here is negative, then that means as time increases, the signal goes down, and we would call this damped. If this lambda here is positive, then as time increases, it is undamped, and it's an oscillation that's growing. So the blue plot here, that entire thing is what we would call a mode. All right, so let's talk about our mode. All right, this lambda term is great, good for physics, good for, you know, things, but the units on lambda are not particularly useful, because if this is a very high frequency oscillation, we want it to damp out faster than if it's a lower frequency oscillation. So mathematicians and physicists have a term that they call the damping ratio, which is defined right here. So as the frequency goes up, then in order for the damping ratio to stay the same, the lambda also has to go up. And if you read any papers or physics books, you will see this particular symbol here. I honestly don't even know what the Greek name is. Anybody know what the Greek name of that symbol is? I'm just going to call it damping ratio. All right, so if you notice, if lambda is negative, the damping ratio is positive by definition. What we will find as engineers when I read papers, they tend to talk about a damping ratio percentage. So if the damping ratio is 0.02 in a paper or in a NERC guideline, it'll say 2%. If you think about this damping ratio, if the frequency is 0, then the damping ratio is either going to be +1 or -1. And as the frequency goes higher and higher, the damping ratio will vary between +1 and -1. So that's a good attribute of the damping ratio. Again, what you'll find in the WEC community, documents on WEC websites, is they're going to talk about a damping ratio percentage. And all they're doing is taking this number, damping ratio, and multiplying by 100. All right, WEC doesn't formally define like what is a signal that's undamped. All that the WEC standard says is that oscillations do not show, or this is when it's a problem. It's a problem if it does not show positive damping within 30 seconds. So all it's saying is lambda has to be negative. Can't be 0, can't be positive. So that comes from that TPL requirement. All right, one comment. Most of you are in WEC, so you're fine with this percentage. I got a little confused preparing these slides yesterday because I also go to NERC meetings, and other parts of the country and other engineers talk about a damping percentage, and they mean something completely different, not completely, something different than this. It's not completely different. So for instance, Southwest Power Pool has a document from 2016 that defines this is the requirement of what is a damped signal. And they say that it has to have a 5% damping factor percentage. And their damping factor, just kind of wave my hands through here a little bit, but basically says that the peaks, let me just go open that. So this is an SPP document. So they're talking about basically these peaks as they go down need to be 5% lower than the previous peak. And that is what they define as 5% damping factor. All right, you can go through some math, and it actually mentions it in the SPP document. Let me go look at their requirement here. They say it has to drop to, to 0.95, so a 5% drop. They do make a mention that, hey, when you're doing modal analysis, Prony analysis is one way to do that. So we'll talk about that in a moment. It says, hey, that damping ratio is 0.008, corresponds to 5%. And I, just went through a little math to show you that on this slide. The only thing that you need to take away from my presentation is when somebody says it's 5% damped, you need to ask them, how do you define that? And make sure that they're defining it the same way as you. So essentially, if SPP says it has to be 5% damped, in WEC, using your terminology, it means it has to be 0.8% damped. And it means the same thing, just a different definition. So just be careful with that. Inside WEC, it seems like people are consistent, but I suspect not every engineer knows in their head what they mean by that. I know I didn't until I made these slides, to be honest with you. So, all right. So the nice thing about the damping ratio I mentioned is it varies between 1 and -1. One of the problems with the damping factor is it varies when the damping ratio is 1, the damping factor is also 100%. But when the damping factor becomes damping ratio becomes negative, the damping factor goes to -infinity. So it has kind of a weird behavior in that direction. So for the rest of the talk, we're going to stick with what WEC uses for terminology, which is just this damping ratio multiplied by 100. All right, so now we've defined what a mode is. So let's go back. We'll look at our picture of our mode. So our modes look like this. All right, so we have a signal now that we want to approximate using modes. So when I look at this, can I make one mode that describes this signal? The answer is clearly no, I cannot. So this signal has more than one mode in it. So what modal analysis is going to do is it's going to calculate a group of modes that approximate our signals. And each mode is going to have a different damping factor or damping ratio, and it's going to have a different frequency. And then in order to approximate our signal, we're going to take a summation of these modes, and it's not just a linear sum of them, it's a complex number sum, because we're going to take this curve, the mode with the damping and the frequency, and we're going to apply a magnitude for it as well as a phase shift. I'll show some examples in a second that explain what the phase shift is for. but we're going to approximate our signal as a summation of these modes. All right, a quick aside, there's some other stuff that goes on as well. Imagine that we had a response that looked like the blue signal here on this slide. Well, that's literally just a cosine wave added to a line. So there's a trend. The term we would use is a trend. So the trend line is 0.1 times t. So it starts at 0 and goes up to 1 at time 10 seconds. So PowerWorld's modal analysis tool, which we've had for many years in simulator, what I'm covering today just uses that tool but packages it in a way that's useful for transient stability. So the modal analysis tool allows you to have a trend that is either a constant, a linear, or a quadratic function. For the purposes of what I've done with the time windows in simulator, we just always do linear for now. We may change that later, but our experience is that usually works good enough. So didn't want to give you another option you have to worry about. That might change, but who knows? But the point is we also include this trending line. So the final approximation for a signal is it has a trend polynomial. For the purposes of this presentation, we're always going to use a line. So the trend C and the trend A are both 0. And then, no, sorry, trend A is not 0. Trend C is always 0. So our final approximation for a signal is the trend line plus the summation of the modes. So the result of doing modal analysis will be to calculate a list of modes with a frequency and damping for each one. And then each signal will have a trend as well as a set of complex numbers that are assigned to the mode. So just kind of an aside. So when you have a summation of damped sinusoidals, it's actually, it never looks as good. I go back to the, if I go back to SPP plots, and I've seen the same thing at WEC meetings where they show this nice damped sinusoid and say, well, let's count peaks and, make sure the peaks are decreasing over time, and I'll get out a ruler and measure the slope and calculate the damping. Well, as soon as you realize that a signal has more than one mode in it, then it gets more complicated. So I just threw together an example here of a signal that is damped, but if I'm looking at it in the 2 to 4 second time frame, I might not think that. So the modal analysis will capture this kind of result. All right, so let's go look now. So I'm going to actually go into simulator here. I've got a couple cases up where I've run transient stability on a little small system. Well, I'll run it now. So I've got a little system here. I'm going to look at the generator speeds. If I look at the generator speeds here, you can see them oscillating around, and we're going to calculate what the modes are for these signals. So if I go in here and I go into the result analyzer in PowerWorld, oops, move those in. All right, so here we have them. So if I come in here and then I hit, sorry. There we go. I was just loading the wrong one. All right, so if I come in here, I've defined a time window. Talk about this a little bit more in a second, but it just says that between 3 and 10 seconds, I want to look at the generator speeds. So if I hit calculate here, it will calculate my results. One thing I can do is I can come in here and I can see the min-max result for these signals. So this is the generator 1, 2, and 3. Here's the max, here, or min, max, time of min, and so forth. So you get this table of summary that I mentioned before. And then I also over here get the modal results that are telling me that there are, let me just hide these. There are 5 modes that it calculated for the time, for the generator speeds between 3 and 10 seconds. And I can go look at a dialog that shows me this calculation. So here we are. I have generator speed at bus 1, and it's telling me that it's got these 5 modes. The mode frequencies are listed here. And the red signal here, sorry, the blue signal is the actual simulation result that I have. And the red signal is the reproduced signal if I take the summation of these 5 modes. So clearly that fit very well in this example. All right, so in the user interface, I can play around and just kind of, see how do these things fit together. So for instance, I could hide all the modes listed here and say don't include them in the reproduction, and then all I'm getting now is the trend line, which is up here. So this is the general trend, and then you can actually slowly add back in the signals as you go. And if I look at a list of signals, if I look at a list of modes for a particular signal, PowerWorld also lists something that we call the rank. All right, the rank I'm going to describe here in just a moment, but it just says which modes are most prominent in this signal. So in this particular example, it's saying that 41% of this signal is the first mode, 28% the second, and so on. And we'll see in a second that that's clear that that's reasonable. All right, but first of all, we have to describe what is the rank. I mean, qualitatively, what I just said sounds great. It's like which modes are in this signal, but how does that actually calculate it? So our modes are made up of these contributions. Our signal for each mode, this is the contribution to a particular signal. So we don't really want the cosine term because that's just oscillating. We want the magnitude. So we really only want the magnitude term. But then we have a little bit of trickiness here, because you could say, well, I don't really want the damping, I just want the magnitude. But the problem is that if it's a damped signal, the magnitude is highest at the beginning, so that's fine. But the magnitude might be very, very small for the contribution from an undamped signal. But because it grows exponentially over time, the magnitude might be 1,000 times smaller than the value at the end of the time window. So what simulator does is we base the rank on the maximum of these 2 values. So if the signal is damped, we'll use the magnitude. If the signal is not damped, we'll use the magnitude times the damping at the end of the time window. And so the rank factor kind of internally will be calculated from that. Simulator will then sum them up and normalize them and present to you a rank that sums up to 100. So that's what this rank is coming from. And so what happens is I can, on this dialog, I can kind of play with, let me just make this bigger, kind of zoom in on this. Oops. All right, so if I go ahead and add the highest ranked value, it's got a 0.1 hertz mode. you can see, yeah, if I only include that one mode, I'm much closer now. The general shape of the response is showing up as the primary part of this signal. The next signal that I have, there's two 0 hertz modes here. So a 0 hertz mode it's just a damp signal. So it's really just trying to match the trend. So if I include both the 0 hertz signals, so now I've included the first, the second, and the fourth mode in my signal, you can see that the result I have of a reproduced signal is kind of following the middle of this oscillation, which makes some sense. Finally, there's a mode here that's the 1.3 hertz signal, and when I include that, it pretty much matches exactly. There is one more mode here, and probably over WebEx, you're not even going to be able to tell there's a difference, but notice that it really only represents a small fraction of the signal. So really, these first 4 modes were the primary modes for this. So the slides just kind of animate through showing you how that works. All right, I kind of skipped over these 0 frequency modes. So what exactly do those mean? So these small frequency, all that modal analysis is a bunch of mathematics. So when we get the results back as engineers, we have to look at it and go, well, what does this really mean? So the 0 frequency modes are really just matching the trend. So if you look at it, the trend line was just a straight line. And what including like this particular undamped 0 frequency mode is doing is it's just kind of bending that line a little bit. So the fact that this mode shows up with negative damping really isn't important for our analysis because the frequency is so slow that, yeah, it's undamped. So after 1,000 years, this signal will blow up. But that's not relevant to us. See, so it's important that you ignore those small frequency modes. All right, the next step. So we've talked about one signal and defining the shape of that signal with a bunch of modes. The next question is, what if I have a whole bunch of signals? And the examples I'll do on a WEC case shortly, I'm going to have 1,000 bus frequencies. So the question is, does that mean I'm going to have, thousands of different mode calculations? And the answer is no. The modal characteristics of your signals are all tied together by the network of the power system. So in this particular example that I'm doing on this little small case, here are my 3 bus or generator speeds. If I go back to plotting, I can pull up my 3 generator speeds, and what I've done is kind of zoomed in on 3 to 10 seconds because that's where I'm studying them. Okay. Clearly, when I'm looking at this, these signals share a frequency. They're literally oscillating at almost exactly the same frequency at 1.3 hertz. So when I do modal analysis, I don't really do it on one signal. I do it on a group of signals, and they all share the same modes. So if you're looking at, it kind of depends what you want to do. So if you're looking at a big WEC response and I want to know what is the global characteristic of how the system is oscillating, then you should pick a signal that will give you that characteristic. So for instance, bus frequency tends to be something that's global in a power system. Something that's not would be bus voltage. If I were to look at the bus voltage of all the load buses in WEC, you're going to get lots of local modes with motors and local generators, and there'll be hundreds of local modes probably. I don't know that for sure, but that's my gut feeling. So, that might be something you want to study, but it can slow these calculations down a lot. So you just have to be careful about what you choose as your signals, and I'll show that in a big system shortly. All right, so modal analysis, the result of it is you're going to get a list of modes. You're going to get each signal is going to have a complex number associated with that mode. So just kind of numbers wise, if I had 5 modes and 100 signals, the modal analysis is going to be calculating 500 complex numbers in the background that describe each signal and how it fits to modes. So as again, they share the same mode. So if I come in to my modal analysis here again, what you'll see is as I click on this dialog on each signal in the bottom right, it's showing me that particular signal's reproduction. And you can see that with these 5 modes, I can replicate these 3 signals. You know, what you're going to see in the WEC case I do shortly, we're going to have 5 modes for the entire WEC, and it's going to pretty much replicate all the bus frequencies we look at. All right, so let's look at some information on here. So I'm going to add as columns in here the modal analysis results that show the mode and angle. Actually, I guess I already have it on here. So this is showing me for all of the modes by number, what is their magnitude and what is their angle as I go through here. All right, and so first of all, the first mode listed is the 2 Hertz mode. I'm going to kind of ignore that because that's the mode that's really tiny and isn't contributing that much to the system. The next mode was that 1.3 Hertz mode that we had mentioned. So one of the things you'll notice is when I look at the angle associated with that particular mode for each signal, you'll see that there are 2 generators that are about minus 110 degrees and another generator that's at plus 69 degrees. So they're 180 degrees out of phase in that particular mode. Well, if I look at my plot, I'm like, yeah, that makes perfect sense because generator 1 is oscillating out of phase with generator 2 and 3, which is exactly what the modal results are showing us. So that's somewhat comforting that, yes, indeed, that makes sense. The next mode I look at, the low frequency mode, which was kind of represented by this curve in the bottom right here, you'll notice that the phase angle for the 3 signals for that mode are all about the same. Well, that makes sense because the general shape of the envelope of this response is what this mode is describing. And they all have the same general shape for that mode. And then the other 2 are the 0 Hertz modes that we won't talk about. But I guess my point is the results of this thing make sense. When I look at a little case, it's like, yeah, this feels like it's doing something useful. So now comes a lot of hand waving. Maybe in a month or 2, we'll have Professor Overby give a talk on how these algorithms actually work. But there are a lot of methods to do them. The Prony analysis approach was kind of the first one introduced to power systems. That was back when I was in grad school in the late 90s. Some work out of BPA, I think by a guy named John Hauer. Though I can't remember for sure. There are more modern approaches, though, that come out of the image compression and facial recognition world, and they have really cool names like matrix pencil and dynamic mode decomposition. I am not going to talk about this. Some terms you'll read are things like Hankel matrix and singular value decomposition. This presentation is not about the theory. I'm just going to show you the answer. So, you know, for now, you can call it what I call it, which it seems like magic. It's like, it definitely shows you the results. And when I look at the reproduced signals, they match. So for me, at this point, I'm comfortable that this magic works. But there's a lot of math behind it that we're not going to talk about today. But we do want to talk about essentially the math you need to understand to use the software. So there are going to be some input parameters that are coming out of these algorithms. And I want to explain to you why they matter. So one of them is something that we all learn as electrical engineers way back in school, is something about sampling. So as an example, if I have this red curve here, if this was my oscillation, it's about a 9 hertz oscillation. If I were to sample that signal every 1 second, which is shown by the black dots on here, then it would look like I'm sampling about a 0.1 hertz signal. So this is what is known as aliasing in the frequency world. So what you need to know is if I want to detect a 5 hertz oscillation, I must sample that signal at least 10 hertz. It has to be 2 times bigger. So what you're going to see in simulator, we'll have a dialog in the time window. I guess I can just show that. There's going to be a little piece of input data when you're doing modal analysis that says, tell me the maximum frequency that you care about. I love this input because it's very, you don't need to understand why, what it's going to do with it, but it makes perfect sense. I care about 5 hertz and less. So when you put in 5, what that means in simulator is we're going to go sample that signal at 10 hertz. And it's because of this. All right. However, the other thing you need to know about these algorithms is what makes them run slow and what makes them run fast. All right, the first thing that makes them run slow is obviously the more signals you have, the slower it goes. So the algorithm that we're using by default is the iterated matrix pencil. That thing happens to scale approximately linear with the number of signals. So if I double the number of signals, the speed gets twice as slow. The big thing, though, is the number of time points. So when I say sampling, you're like, well, we sample at a quarter cycle because that's what we're running our simulations at. But a quarter cycle would be 1 every 240 seconds. So that means we'd be sampling at 240 hertz. So we'd be able to pick up 120 hertz oscillations. But we don't even care about those. So why would we sample that much? So in the algorithms for finding modes, we're going to do much, much lower than that. And it's a good thing because the fewer time points we use, the calculations scale cubically. So if I double the number of time points, so if I double the frequency that I care about on this dialog, the calculation runs 8 times slower. So that's important to know. The other thing that happens is once you have the modes, we then run another algorithm that calculates all the complex factors for those. And the thing you need to know about that is you don't need to include all the signals in the modal calculation. You can still fit a signal to a list of modes regardless of whether it was in the calculation. So what's useful to you? First of all, don't use too many time points. Second of all, be careful choosing your time window. I'll show an example in a second. And then I'll show the iterated matrix pencil in a second too. So if this is my signal, if I choose a time window between 0 and 10 seconds, that is foolish because I'm trying to fit this discrete jump here at 1 second. The algorithm actually works surprisingly well. It's kind of funny that it works, but it's providing some somewhat nonsensical results as a result. So this is the final fit for that, which looks okay. But if you look through as I add the modes in, so there's the linear, there's a piece, there's another piece I'm adding in, I'm slowly adding in signals, and I've got it fit pretty well now at the end. And then it adds in a couple more modes that just sort of magically cancel out the first second of it. But those aren't real. This was bad user error here, putting this in like that. It would have been better to pick a window that started after 1 second. So choose your window wisely. Sampling, I already mentioned. Actually, usually when I play with this tool, I tend to use 2 hertz because we're not looking for modes that are faster than that in this tool usually. And setting it lower is going to make the calculation faster. All right, the other thing to realize is there is an option on the modal calculation that says how many iterations should I do? All right, what that is the matrix pencil routine. It scales with the number of signals. So if I give it 1,000 bus frequencies, which I'm going to do in just a second, if I were to run it on all those signals, it'd be slow. I think it would actually work, but it might take a few minutes to run. And we don't really need to do that because those, as I mentioned before, those signals all share the same modal information. So what the iterated matrix pencil does is it picks one signal, adds that to a list. It performs this magic calculation to find the modes, calculates the complex factors to fit those to the modes, and then it takes the list of the signals that you have left and picks the worst fit, like which, the signal that I included in the modal results is going to be a really good fit. There'll be a generator somewhere else that's a very bad fit. So then we'll say, well, why don't we take that really bad fit, include that in our signal list, and rerun the matrix pencil with 2 signals. And then we'll take the next worst one, rerun it with 3 and 4 and so on up to the max iterations. And that is the number that you're specifying here. All right, so implementation in the software. So in the software, this right here, you have to define these time windows. This is the time window definition. So a time window up at the top, you're describing, start and end time. And you can also say, treat those as a delay from the last user event. So I could say start 2 seconds after the fault clears and go out to 12 seconds after it clears or something like that. The next thing you have to do is say, what signals do I care about? You can either, kind of like transient limit monitors, pick, I want generators, I want speed, I want all of them, or a filter, or whatever you want here. Or you can actually go just pick a plot and say, I want the signals that are on this plot. So if you've already defined a plot, you want to do modal analysis on that plot, that's easier to do. All right, then down at the bottom, you have these options we've kind of already talked about. And then I mentioned the iterated matrix pencil, you start with a signal. If you don't tell us which signal to start at, we just pick the first one, which is probably the one with the lowest bus number. But you can also tell us, you know what, this Grand Coulee plant, I always want to know about that, so I'll pick that. All right, and then I'll get to those 3 things shortly. Anyway, these slides you can read through later. Scott will put them out on our website. So let's go look at running this on a really big case now. So all right, this case right here is a large WEC case with 22,000 buses in it. I've run a particular outage that we all run all the time to take 2 big generators out. If I look at the frequency results, here's a list of every generator that's above 50 megawatts in their, this is the frequency at those buses. Just pull that up. So that should be a familiar looking plot. I think this WEC case is about 6 or 7 years old, so maybe it doesn't look like that anymore, but this is the general response of 1,000 bus frequencies in WEC as they go. It's always an interesting kind of get the response right away, the stuff that's delayed about, 2 seconds, 3 seconds is Alberta, which ends up swinging the most. You kind of come back up and come up to a new frequency. So there's some bus frequencies I care about. In addition, I've created a plot that has every bus voltage that at 300 kV and higher, and I'm going to plot the deviation from the initial. So we'll look at this point and we're going to calculate modes on these values as well. So there are your bus voltages in response to this fault, or not fault, in response to this 2 generators tripping. So we're going to look at the frequency analysis for these things over a window. So we're going to look at frequencies from 20 to 30 seconds, and we're going to look at voltage deviations from 5 to 15 seconds. Right. All right, so come over here to the result analyzer. I've got right here, I pull, in this case, I use the plot. I said, just pick the data out of this plot. I'm only looking for 2 hertz and lower in this example. And when I hit calculate here, it's going to go and calculate all these modes. Right now, there are no modes calculated. So I think this takes about 8 seconds. 1, 2. Yeah, so it took about 8 seconds to calculate all those modes. You know, if I had put this max frequency in there at 20 hertz, it would have taken about, well, it would have taken several minutes. So, because setting it, yeah. So you double that value and it gets 8 times slower. So be careful with the settings that you're looking at. Again, I can get statistics. You know, if I only want to look at voltage, I can look at what's the max and the min, what's the max minus the min. It's saying this bus has the biggest deviation, so 45,040. I can go look at a plot of that. So this is the biggest dip. I assume that's near the generators. All right, then I can go to damping. So if I go look at the modes, what you'll see is, miraculously for voltage, there are only 5 modes. And I can go look at frequency. There are also only 5 modes. If I go look at my signals, so right now I'm looking at, 1,084 signals. And let's say that I want to look at, there's a value here called the cost function. The cost function tells you how close the match is. So if I set this here, if I sort by the cost function, if I look down here, these all match nearly perfectly. Oops. These are all almost perfect matches. But even the worst match in the entire system is right here. So I have reproduced that signal. That's pretty close. I mean, it's not exact. It's slightly different, but it's very close. So that tells me if that's the worst one, that's a good match. And in this particular case, this is the worst frequency match, and this is the worst voltage match. And again, it's not perfect. At the end here, something's a little off, but it's very close. One other thing that's kind of interesting here, I used bus frequency and I used bus voltage. And if you look at the frequencies that it calculated, again, this feels like magic to me. They're close. There's a 0.22 hertz, there's a 0.32 hertz, and there's a 0.61 hertz value. And the damping are at least in the ballpark of each other. The bus voltage, you'll notice it picked up another mode, but I did run if I look at bus frequency a little earlier in the simulation, like from 5 to 15 seconds, it also picks up that mode. So I suspect that this is just a mode that kind of dies out before 20 seconds. So the modal analysis after 20 seconds is not picking it up. And, go read some papers. There's papers on the WEC website that have done modal analysis on PMU data. It's not even simulation. They talk about there's a 0.25 hertz mode. That's the north to south mode. That's right here. This 0.22, this is the north to south mode. It says the damping is between 10 and 15 seconds, or 10 and 15%, so it's close. There's a north-south mode B, which is with Alberta. That's about 0.4 hertz. I think that's really this 0.33 hertz value in this example. And then there's a mode that is with BC Hydro that's about 0.6 hertz, and that's also showing up. And you'll get similar results if you look at any of these links. All right, so now the question is, I have all this data on these signals. What am I supposed to do with it? So what Simulator has done at this point is we just have a screening tool where you say, when should I consider a signal undamped? So you can say anything below 4% damping, but don't include these low frequency modes. I talked about that before. The really low frequency modes are just giving you the general shape of the curve. They're not really looking at the damping. They're picking things up that you really can't see. And then also only tell me about it if it contributes a lot to the signal. So if I come over here, there's a column on signals that says, does it have an undamped mode? And they're mostly set to no. Oops, I think I have to change. Yeah, if I change this to 5, then one of them will show up as yes. There we go. So it depends on these thresholds. So what you'll see is there's a list here of a few modes, these top 13 modes that are showing up as undamped. So let's go look at one of those. So what it's saying is it has this particular mode that has a rank higher than 10%. And so it's this 0.6 hertz mode is the one that's undamped. I mean, it is damped, but it is not damped enough because I said it has to be at least 5% in the input data I had. So what our thinking is you'll be able to use this to kind of screen to then go look at which signals have the least amount of damping. Again, WEC doesn't describe a minimum amount of damping, so maybe you set that damping percentage to like 0.5 or something, just to say, the damping is negative. And only look at those. All right, so this kind of works. All right. So let me just show one last thing, because I did run one other simulation this morning. So I ran another contingency where I faulted something for 12 cycles. I faulted a 500 kV bus for 12 cycles, just to kind of really knock the system around to get some more modes to show up. And I call that the 500 kV 12 cycle fault. And I already have results in here. So I'm going to come in. And I know that I need to go from all right, we'll go from 2 to 20. Let's just delete these. All right, so I've got these faults right here, and I'm going to calculate the modes. All right, so I get modes here, and I'm going to pick up a whole bunch more modes. So I'm still getting those 0.6, the 0.5, the 0.35. I'm getting the similar modes that we had with the other outage, but I'm also getting these higher frequency modes. And what I wanted to show you was you can look at what is the rank of a particular mode, and you'll see that the rank of the first of this mode right here is really just with 3 generators here, and then it gets smaller and smaller as you move away from it. And then I went and looked at those modes. I made a plot. It's these generators right here, and I plotted their megawatt output. And it's not that easy to see here, but you can kind of see that they're swinging against each other. You know, the green's going down, these guys are going up, and they're swinging back and forth. And if I go look at the bus view around there, let's see. What's going on is there's a little system hanging off of Rio Oso here with three different generators on it, and those 3 generators are swinging against each other, and it's picking that up. And that is a very local oscillation because those are really the only generators that have that frequency in their result. So it picked up a local mode at about 1.4 hertz, which, you know, what literature tells you is that local modes are, 1 to 2 hertz, and it found those. And all of these modes in here, when I looked through them this morning, are like that. They're little local modes. They didn't show up when I tripped 2 big generators because it wasn't a big enough kick to the system. But a 12 cycle 500 kV fault was enough to excite those local modes. So I thought that was interesting. So the future work of this, just kind of finished putting it in version 22, and also maybe automating some of this result analysis at the end of, like, maybe report violations of any signals that would get flagged as undamped. That's not there yet. You have to take the results and run this and look at it yourself, but that could be automated. And there's a lot of cool visualization that you can do around this as well. But in the interest of 1-hour web videos, we will stop at this point. So there. All right, so I guess I open it up to questions that people have. I can answer them, or Dr. Overby could answer them too.
All right, thanks, Jamie, for that presentation. Not hearing questions or seeing anything up on WebEx. Tracy just asked a question about this will be posted, and yes, these slides will definitely be posted probably later on today. We will also make available this training video through WebEx, or not this training video, but this client conference video. I'm sure that this stuff will work its way into the PowerWorld simulator training slides, probably with the next time that we do training on the transient stability tool. It'll be part of the larger training surrounding the transient stability tool. Okay, so the next presentation we have is from Scott Dahman. Scott is going to talk about the GIC tool and some of the advancements that have made in the GIC tool. So Jamie, I think you have to stop sharing your screen. There you go. And then Scott, I have you designated as a presenter, so you should be able to share your screen right now.
Great. Let me get that set up, and then we'll get started. Okay. Mark, can you verify that my screen's being shared, the presentation here?
Yep, I can see the PowerPoint.
Okay, great. All right. Thanks, Jamie, and thanks, Mark. My name's Scott Dahman again, and most of you probably familiar with me. I spoke a little bit last week as well. Today I'll be presenting and just sharing some of the enhancements that have been made to our GMD tool. Let me see if I can get this on a slideshow presentation. Okay, yeah, first an acknowledgement. A lot of the content in here was actually developed by our co-founder, Tom Overby. And of course, many of you may know he's currently a professor at Texas A&M. There he is in his Aggie gear right there, and some links to his research. And Tom, of course, is still active as a part-time developer and innovator, probably more of a full-time developer in the summer, especially in a COVID summer. I'd say he's probably heavily involved right now. And what we're going to talk about is just a few changes that have been made to better handle non-uniform time and spatially varying fields. So everything that we talk about in here is actually also available in Simulator 21, except the ability to save the electric field data. That requires a change in the binary file PWB file format, and that belongs only to Simulator version 22. Once the version is set, then the binary file format doesn't change. So you could still load all the information in pretty much the same way in 21 as you can in 22. So what we had to do just kind of behind the scenes to make this work is we updated our binary non-uniform field format, which has the extension B3D, to a version 2. And it allows us to read in data that's specified in geospatially kind of arbitrary points rather than from what looks like a rectangular grid when it's projected into like a Mercator plane. So in other words, like constant latitude and longitude spacing was the format that we had to use before. Now the points where a field, E-field vector is specified can just be arbitrary within a space. So also just kind of behind the scenes, Delaunay triangulation algorithm is now used to interpolate the surface electric field between points where the input is specified. And for uniform fields, of course, this doesn't matter for fields that are like, constant everywhere. But when you have a situation where you have a set of points where the field is specified, then what do you do to interpolate between those? That algorithm has changed a little bit. And we can talk a little bit more about that at the end if there's time, and perhaps if Tom's got anything to add on that algorithm, we could address that later too. So this discussion is going to deal with like what's primarily done in the calculation mode within GIC under time varying electric field inputs. So the single snapshot mode is for uniform fields only. So if you need to do the NERC TPL kind of standard uniform field, you'd use that. And by uniform, I mean constant vector direction, at least. It can be scaled on the single snapshot mode based on things like geomagnetic latitude and also the Earth resistivity regions. So you can have different scalars applied to that, but generally it's uniform in terms of you have a constant direction for the E-field vector. The second mode can be used with uniform fields that vary by time. So at different time points, you can set up a different uniform field, or you can also have non-uniform fields be specified there. But usually if you're reading in a non-uniform field from a separate source, from a text file or from a binary file, you would use the third calculation mode to get that there. So I'm going to change my pointer here so it stays on the screen. So yeah, we're mainly going to be talking about changes for how the inputs are handled here. So this is the input screen. We have a few different new file types, which we'll talk about in just a moment. And as I mentioned, our binary format for the non-uniform field, the B3D, has been updated. That's kind of transparent to the user, though, kind of behind the scenes. So just a note on terminology, too. We talk about 3D models or 3D inputs, 3D Earth models, and actually the binary file format extension B3D has the 3D in it. Just to clarify, that refers to the Earth conductivity transfer functions. It's a 3D Earth model as opposed to a 1D Earth model that just looks at layers of Earth conductivity as you go from a point straight down towards the center of the Earth. The 3D models are a lot more complex, and they're just now starting to really be, well, they have been through the EarthScope project for several years. This was an NSF-funded project, and there's some successor research that's going on now because I think the NSF funding for that ran out a couple of years ago. But basically, what's done there is measurements are taken that look down into the Earth, not only straight down, but in all directions as well, to compute a better transfer function that's then used to get the electric field function from the magnetic field function. So the E-field vectors that are actually input into simulator are always 2D in the sense that they have an eastward and a northward component. So that's the input that we actually work with in PowerWorld Simulator. Presently, we're not taking as input a magnetic field signal, and then we're not convolving that against the Earth's transfer function, but rather we're taking as input the E field. So simulator doesn't really care if the Earth model that was used to produce the non-uniform E field was 1D or 3D. The input looks the same. So previously, simulator has for quite some time actually supported this type of non-uniform input. This is looking at it in a text file where there's 10-degree spacing that starts at -135 degrees longitude and plus 25 degrees latitude. And then at different time points, time 0, time 1 in this case, there's a specification of the E-field vector at different points on that grid. So, and then again, the grid is defined by these parameters, which are up here in the header. The grid always had to be kind of uniform spacing, although you could have different latitude spacing and different longitude spacing. In this case, they're both 10 degrees. But it had to basically look like a rectangle when projected onto a 2D plane. So now we have the ability to take arbitrary points, which makes the file format a little bit more complicated, and also makes in a text file format, it's a little bit wordier, but at the same time, it's reflective of the data that's being produced by industry. And we'll look at some examples on that too. So the NOAA, the National Oceanic and Atmospheric Research Organization, has got some near real-time electric field data at 2 degrees spacing. It is kind of uniform spacing, but it's not a rectangle in that it follows the contours of the continental United States. So there are gaps where the national border is with Canada and Mexico, and then also with the oceans as well. So that data can be accessed here. The files have to be downloaded into a local or network location before you can read into simulator. We'll take an example. We'll look at an example of that in just a moment too. So in simulator, you can load in multiple time files in a single step. They also have some newer data that they're planning to go live with in September that uses 3D transfer functions. So again, simulator doesn't care whether it was a 1D or 3D, but it's just a matter of what data is available. So we'll take a look at that also. So here's the text file format that NOAA produces is GeoJSON. And it's a little bit more verbose. Actually, it's a lot more verbose than what we had before because the points are arbitrary. But here's a point at minus 81 degrees longitude and 24 degrees latitude, and the X component of the E field, so the eastward component and the northward component of the E field, and then just some metadata about the measurement as well. So quality and then the nearest magnetometer from which that data was estimated. And then here's the second point and then the third point with the same kind of data. So let's switch over to simulator right now. And within the GIC form, if I go to the time varying electric field inputs, this is where you can specify the data that can be input. So we have a binary file format, and usually it's a good idea after, if you fetch data in these text file formats, to convert it to a binary before you do analysis on it, because it's a lot faster and a lot more compact. So you just would have to then read it once, and then you can store it in that format. But if I go out to, first, let's take a look at what's on the NOAA website. So this is a link. Let me refresh this here. This was the first link that I shared on that previous slide. So this is just a list of the GeoJSON at 2x2 grid. And the file name, embedded in the file name, is a date and time in UTC, and the date 2020-07 for July 14th. And then, so here's the time code. And then if I click on this, I can open, okay, yeah, this has this is like sorting everything by field and attribute for the different points. And if I look at what it looks like in a text file, it just looks like this. But you can download this. Let me go back. You'd have to download these files basically and save them to a local drive. And then once you've done that, then, let's see, I don't have it here. So here's a set of downloaded files that I grabbed. And then from there, we can go to simulator and just choose to load. And I'll find that directory here. So you just point to one file, but you can also tell it right here to load just the selected file, or these next two options refer to time points that may have already been loaded in a previous operation. So down here, you can just load everything that's after a certain time or everything that's before a certain time. And then you also have the option to clear everything on load or merge the new data with maybe what had already been in here before. But down here, we can just kind of browse what we read in. Here's the date and time string. And you can choose to look at it either in UTC or on your local time zone as well. Although actually down here, it's still UTC, but up here, it tells me what the starting time is in my time zone. So with each time point, it gives you kind of some summary data, like what's the maximum field. And the units in the NOAA text files, the GeoJSON files, are millivolts per kilometer. So we express them in volts per kilometer. And of course, if there's not really a storm going on, then these are all going to be really small numbers. You'd expect that. So I can browse the time points here. If I click on any individual time point, then I can see the geospatial data that corresponds to it over here. So once that's loaded in, to do anything with it in terms of power flow or transient stability analysis, you would need to convert it to the time varying series voltage input. So that's really the equivalent DC voltage bias on each transmission line. And we give you options to automatically do that, or if you want to do it only for a subset of the time points that you loaded in, you can specify those over here. And then kind of need a wider monitor to show the whole dialog here, but you can set it up based on a certain start or end time. And that corresponds to the time that's shown here, not the actual date and time. So if we've automatically converted that, then when we go over here to this mode, then we'll see for each of the time points, the corresponding input voltages on each transmission line. And you don't really, I mean, you could edit those if you wanted to, but they're mainly just there for reference. With this kind of input, then we can include the GIC and power flow, and in transient stability, you can change the time, and it can be an interpolated time that's between time steps too, and then click calculate GIC values. And then you can just use the tool like you would in any other calculation mode. If it's a uniform field or anything else, you can look at the actual GICs on transformers, substations, and so forth. And if it's incorporated into the power flow, of course, you can use those tools where I can go in and solve the power flow and look at the losses, the Q losses that are due to the transformer saturation. So other kind of neat features related to this, if we go back to the one-line diagram, in our contouring now, this is a new feature that was added with this. We have a contour type object that's called spatial data. So all of our other contours that we've had to this point require you to basically put power system objects on the one-line diagram, and the contouring is done based on the location of where those objects are placed. So you can have buses or substations and contour voltage. And if you're in a part of the map or the one-line diagram where there are no buses and you're contouring a bus object, then there's really no data out here. So you're getting an interpolated value that's based on different algorithms. We'll kind of come back to that a little bit later too, but the spatial data is basically just contouring on the geospatial area of the one-line diagram without there having to be an object there. So this is a feature. If you have version 21, which of course most people do right now, this feature looks like it's available, but you'll have to get the latest patch. The next time we update our patch, there will be a bug fix in that. Like currently, if you try to use this in version 21, it causes an error. So I've got the 22 beta going right now, and it should be all good. So if you've got spatial data selected, then basically there's 4 GIC related fields that are available right now. This is something that we could use for other quantities in the future, but right now this is what it's used for. So if we put in magnitude, then we can calculate those, and then you see it's contouring basically everywhere on the one-line diagram where there's data. So that's available right now, and we could change. It looks like. So we get a little bit better contour with that range right there. So this is the data that we actually read in that corresponds to the time point at 80 seconds. You know, I can change this to say 120 seconds, recalculate the values, and then update my contour. So it might look a little bit different, and so forth. So you have those tools available. Back to the data that's available from NOAA. I mentioned on this slide right here that they are starting to put out some new data based on the EarthScope transfer functions. It's at a different website that you would go to. So if I follow that link right there, I'll land on a page that looks like this. And I don't know if this is the most current. Yeah, it looks like this is being updated or being refreshed on its own. So the EarthScope data, at least right now, they started in the Northwest with developing it and then moved to like some other regions across the country. And the southwestern part of the country is kind of the last ones that are getting mapped out on that. So there's a hole down here with this data, but eventually that should be filled in. But if I come down here to the data tab, then it gives a couple other options. And the 3D, see, I think it's this one right here, which will give you a half-degree grid spacing GeoJSON. So yeah, here it's similar to before, except for it's a half-degree spacing. The fields are derived from the 3D EarthScope transfer functions, and it also doesn't include the Southwest. But if I can load some data from that source over here in Simulator. And let's go back to our field voltage input for time varying stuff. And I'll just clear everything out and just load in some different data. This is the half-degree data. I just downloaded 3 files for that. So anyway, if we click on a time point there, then we can see, yeah, we've got half-degree spacing on that. But also, if I recalculate on this and look at my spatial contour, yeah, there's some missing data down here. So that's the shortcoming of that. But there's much higher resolution. And the fact that it's using a 3D Earth transfer function also gives you a lot more of these boundary regions too, where you have some high resistivity regions and lower resistivity regions as well. So those are some good resources that are available now that we can now directly use in PowerWorld Simulator. And the rest of these slides, we'll put these out here. I'm not going to spend too much time on them because we kind of went through the demo, but there's some other slides in here that just kind of give you a how-to on using that dialogue. So some of these things we mentioned already, you can have it automatically wipe out anything that's in there, or just load certain time points and merge them with other ones that have been loaded before. And you can also either create time varying series. So again, these are the equivalent DC voltages on all the transmission lines. That can be done for everything that you load. Or if you want to decheck that box and then put some parameters in here, you can do it. You know, if you loaded in a whole bunch of files, but you don't want to wait for it to generate the inputs for more than just say maybe a few minutes or hours worth of data, then you can bound that and put in a sampling rate. Usually it kind of makes sense to put a sampling rate in that matches the data, because will interpolate between time points anyway. You don't necessarily need to add another one, and you probably don't want to skip over time points for which there is data. So normally you would just match this to what's in the data, if it's 60 seconds or 30 seconds or whatever. And then you can set that up. And then, yeah, we just kind of mentioned some things about the time zones. And yeah, they're just other aspects of that dialogue and some other functions, like changing the start date and the time 0 to the current time that you're on. You can do that. So yeah, I'm just browsing the data and so forth. And then just a little bit on the contouring. So we mentioned that interpolating between, for the E field between points, is now using the Delaunay triangulation method. Contouring gives you an option that we previously in Simulator for the last 25 years or however long it's been, we've used Shepard's method for contouring. And this is kind of an example of how that looks. The influence region on this screenshot is a little bit smaller, so there's some dead band in between there. This looks like it's about a 2x2 grid. But that's one method. The Delaunay triangulation basically divides the space in between the known data points into a bunch of triangles and just determines within that triangle what the weighting of each of the existing points and how that it impacts the point. So you get a little bit different angles in between points. And this is what we're using internally to determine the geospatial E field at points where it's not specified. So that's about all I had for the presentation. Now, if anybody's got any questions, we can address those right now. And again, the slides will be posted later. Mark, can you see if there's anything on the chat window? I'm trying to open my chat window right now, and it's
No particular questions on the chat window.
okay.
Tom, did you have some comments?
Can you guys hear me?
Yeah.
Yeah, sorry, I lost internet there for a while, but I don't have any comments other than we did add that the geospatial stuff specifically to show the GIC, but if there's other things that people would like us to contour, it's probably possible to do. The issue with the geospatial stuff is we don't have objects on the one line, so we have to pull the data from somewhere. And in the case of GIC, we're pulling it from the GIC data that you're storing, which Scott showed. One feature that Scott didn't show because it's very new is we also now show the contour points so that you can see the points that are being used to define the data. Because when we started out doing it, we got these great Delaunay triangulations, but we didn't know how many data points we had. And then just recently, we've added a dialog. So if you click on one of the data points, you actually see information about the data, like its latitude and longitude and the value. So we try to make it very interactive. That's pretty much all I had on that.
All right, thanks, Tom. In the remaining time we have left here, we're going to go back to Jamie, as Jamie's got a few slides on visualization stuff. So Jamie, if you want to share your screen, and Tom, you can comment on this stuff too as necessary.
Okay. Let me get back to it. I just wanted to show it. We don't have this integrated very well into the tool yet, so I don't want to walk through the mechanics of it on WebEx yet. But I just want to give you some ideas of visualizations we'll be able to do with the modal analysis results if you had geography. So these are just some pictures I'm showing. So this is, we've done a calculation of modal analysis on a synthetic grid. So this isn't actually the Texas grid, but we calculated the modes of an oscillation in this fake grid. And if you put arrows on the screen with an angle representing at that particular generator, what's the mode, magnitude, and angle, you can get pictures that look like this. This is kind of a mess. So Tom came up with a way to kind of, we call it pruning, which is get rid of some of the arrows so that there's not too many in one place. And now he's also coloring them based on, I'm not sure, Tom, what's the color here?
Well, the color was just based on angle.
Oh, okay. So it's just, all right. So it looks
Yeah, and
cool.
that requires using a circular color map
Yeah.
because when you get to minus 180, that's the same as plus 180. So your colors have to wrap around. So
Yeah.
we do have circular color maps now too.
Yeah, so you can get, this is a mode that's kind of oscillating around Texas. This is a mode where clearly there's a generator down here generating that mode. The arrows are all kind of coming through and out of here. You can also do things like if you calculate the mode or the modes for voltage, you can take the magnitude and angle of those modal calculations and treat them like real voltages and angles and sort of approximate how that oscillation is causing power to flow around the system. And you can kind of get from that, I don't want to walk through all this, but you can calculate the source of an oscillation. This was an example where Tom had put in a fake generator intentionally creating an oscillation, and the modal results kind of pick that up, and you can kind of blame it on a particular generator. Actually, it'd be kind of cool if there's a feature in a control room with modal results where you could hit a big button that says blame, and it would pop up which generator is causing a problem. I don't think we're there yet, but there are some things that we can do with these modal results that we're not, we haven't completely integrated into the tool yet, but are looking at doing. Is there anything else you wanted to add on this, Tom?
No, I don't have anything else to add.
Yeah, I just wanted to show there's a lot of cool visualizations that you can use with this modal analysis results. So, all right, that's all the extra stuff I didn't cover at the end, Tom or Mark.
And just to be clear, Jamie, these arrows and such are available in the geographic data views.
Yes, those are showing
GD.
up in geographic data views. That's correct.
Okay.
Geographic data views have a rotation angle, and you can trying to remember where the arrows are at, but yes, you can do it with those.
And so if anybody isn't familiar with geographic data views, they are a way to visualize geographically a bunch of different things and change sizes and colors and so forth based on their parameters. It's not probably a very heavily used portion of our tool, but we encourage you to take a look at it because lots of times you can get some really neat visualizations out of them that give users a good idea about the state of the system.
Yeah, especially as people are finally populating large people entities, you're going to have it. If you pull up a work case, there's a decent amount of information in the standard base case now.
Yeah, geographic data. Yeah.
Yeah.
Okay. Sounds good. Well, with that, I think we are ready to conclude this particular session of our users group meeting.